So I was recently invited to give a talk in Hanover at the conference for graph databases in general, and that session wasn't recorded, so we're doing it here now as a webinar. And when I went to this conference in Hanover, I had kind of this ambiguous feeling that on the one hand, AllegroGraph is viewed as a graph database. On the other hand, when you see overviews of graph databases, you sometimes don't see AllegroGraph in this thing. And it seems to be kind of an opinion that RDF databases are not graph databases. So, for example, if we look at a Twitter like this from Achim Friedland, I said, well, AllegroGraph does not implement a property graph. It's not a real graph database. Or Marco Rodriguez, the evangelist of graph databases on our planet, says, well, you know, there's a technical difference because RDF stores use indices and graph databases use traversals. So even in Marco's mind, there's this split between graph databases and RDF databases. But then sometimes you see that triple stores are included in graph database projects. But I want to talk this morning about AllegroGraph as a graph database, and I actually even want to convince you that AllegroGraph is even better than a graph database because it can do some things better than graph databases. Okay, so what I'm going to talk about is AllegroGraph as a quintuple store. I'll just say a few words about AllegroGraph as an RDF store, and then most of the time I will talk about AllegroGraph as a graph database. At some point I'll talk about the AllegroGraph architecture, and I will talk only about one use case. And then I have to apologize in advance. It's going to be slightly more technical than I usually do. So more code will be flying by, but I'll compensate in the next one. Okay, so let's start with AllegroGraph as a quintuple store. Yeah, so just forget about RDF. Basically, AllegroGraph is a huge set of triples with a first slot, a second slot, a third slot, and a fourth slot. And every tuple has a unique ID, and every tuple has a transaction number. And these slots can be really any data type. So I can say 1, 2, 3, 4, and I would have a tuple. I can say date after this date, and then I give a telephone number. Yeah, or Jan's Last Pizza in file 1, and the tuple number is number 12, or the tuple number is number 12. And actually, I can even do reification this way. I can say no one believes number 12. So no one believes that under some interpretation of this tuple, you could say, hey, this is a reified tuple, or you are a reified tuple. So in this quintuple store that we have, we do very efficient geospatial and temporal representations. You can sort these tuples in 24 different ways. Sorry. Default is six indices, but you can control whatever you want to do. These tuples can be sorted on ranges for all kinds of data types, and because every part of a tuple can be a long string that we internally replace by a unique number, but we can do free text indexing on the strings. And if you want to do super fast graph search in your tuple space, then we'll give you some special caching techniques, neighborhood matrices, adjacency lists, and UPI maps to make your queries go much faster. So let's look at this as a AllegroGraph architecture. So usually this picture here is completely blue because I showed how from the bottom up AllegroGraph is working. But just for fun today, I colored everything green that actually doesn't care about AllegroGraph as an RDF triple store. Yeah. So we have a normal storage layer that does column-based compression on the tuples, all kinds of indexing, and on top you have session management like in any database. And then on top of that you have the rich set of features for AllegroGraph, but only Sparkle will be deeply, deeply unhappy if you have a tuple like 1, 2, 3, 4. Yeah, but Prolog doesn't care about whether you have a tuple of 1, 2, 3, 4. Then we have a new common logic interface that is kind of built in with RDF inside. So I will give a talk about this at MTech and a webinar real soon. But that's kind of RDF dependent. Then all our other features like geo and social network analysis and temporal reasoning, again, are completely independent of RDF. Obviously, our RDFS++ reasoner is RDF. And then we have a JavaScript stored procedure language running in the server, and again, that's completely independent of RDF. And everything is available through a REST interface. And then we have a whole bunch of languages. I don't even have all these languages here up on top, but obviously the Sesame and Jenna layers are deeply RDF-based, but all the other languages, again, are partly RDF-based, partly completely independent of RDF. Yeah, so again, AllegroGraph is a tuple store, and we don't care about the RDF part on the lower levels. Now let me just give you a little demo about this. So what I'm going to do is I'm going to go to my Ubuntu box. Yeah, and just let me start a tuple store. So on the right hand side you see some Lisp. So everything I do here in Lisp, by the way, you can do in Java, Python, Perl, or whatever you want to do. Lisp happens to be my favorite language, and so, oops, it's already open. Let me do a reset, close all tuple stores. So now make a new tuple store. Let me get some water. So now I have a tuple store open, and let me add a tuple. Yeah, I can say just add 1, 2, 3, 4. So now I have a tuple 1, 3, 4. I can say Jans works at Franz, or Jans' hair color was blonde in 1969, now entirely gray. Or I can say Jans, and the predicate would be 122, a string blonde. And I could use Prolog to look at all my different tuples I have so far. But more fun is to create a big random graph in the tuple store just with this little code. So I'll create 1,000 edges where the vertex can be any number, a random number from 1 to 100, or 0 to 99. The predicate can be a random number, and the object can be a random number. So I'm creating, so now I have these things in memory. I do the tuple store, and now I can go to our graph browser. So let me look at this. So let's look at a typical node. So I take 30, and here you see that 30, well, this is of course an RDF browser, so I'm showing you the graph. So 30 has these properties, and these are the reverse properties, and I could click on number 66, and 66 has a 34 predicate to 54, and 54 has a 52 predicate to 43, and I can go back to the graph, and here you see part of the graph. Yeah. And then just for fun, let me get another graph here, sorry, another vertex. I put it here, and then let me, what I do now is I look at some of the predicates that I will use for some graph search. So let me just do random graph search, a random set of predicates, and ingoing and outgoing. So it doesn't matter, just entirely random. And now I can say, first let me do this. Yeah, so I click on 30, I click on 85. I'm kind of exploding the graph, and maybe at some point I will get to 62. No, it doesn't work, so let me see if I can get from here to this guy here. And I can't, because somehow, given the predicates that I chose so far, there's no link. So let me add some more. Let me see if I widen the number of possible predicates between things. And again, it's random, so I never know when I get lucky or not. And so now I saw that I got a line from 62. Yeah, so I can take anything else. Just let's find some random node here, 23. Let's see, can I get a link? No. So I actually probably have to choose even more here. Predicates. And now would there be a link? No, it's actually, okay, let me do select all. Can I now find the link from 23 to the 30? Yeah, now I can find the link. So anyway, as you can probably imagine, this has got nothing to do with RDF. This is just a tuple store, and I'm just interpreting as a graph, and I can use my graph algorithms to do, for example, a shortest path analysis. So let me go back to my presentation. So AllegroGraph's tuple store. AllegroGraph is obviously also an RDF store. So we adhere to, if you adhere to the RDF conventions by having your subject always be a blank node or a URI, your predicate always a URI, and the object of your tuple a string, a URI, or a blank node, then you have an RDF store, and Sparkle will be totally happy. Right now we support Sparkle 1.0 and some of Sparkle 1.1, and in the fall we will have everything in Sparkle. And then on top of that we have an RDFS++ reasoner, well, all the things that you expect from that you already know about AllegroGraph. Okay, then let me go to AllegroGraph as a graph database. So people say that, well, tuple stores are not graph databases because they don't have properties on the edges. Yes, that's to some extent true, but on the other hand, tuples actually have a fourth element. Well, actually, RDF tuple stores are nowadays always RDF quad stores. And with the fourth element, we can actually even do hypergraphs. Yeah, we can, if we want to say that, look at this picture here, we say Jans loves pizza. And actually, this is wrong here. I just draw this thing. I wasn't done with this one. So basically, I'm saying, if you look at the predicate loves, then there's the weight 90. Yeah. So according to my mother, I really love pizza, and according to my wife, I have a very low weight for a pizza. Yeah. So I can present properties of edges using the fourth element. Yeah, and I can even go hyper. So I can again have properties on sorry. I'm now mixing the graph language with the triple language. Anyway, I guess you get the point. Okay, so now let's look at a comparison between various graph databases. I recently saw this this thing in a blog on the web, and I looked at this list, and I didn't see AllegroGraph in this list here on the top. I saw Neo4j and all the other ones, and I guess the one thing that's in common is that it's Java databases, and then there's a lot of things here. And so I said, okay, let's look at the software it's written, utilities, the language bindings, etc., and let's see how AllegroGraph does on all these particular things. Yeah, and notice if you look at this, that Neo4j probably has the most yeses in all these columns. So I went through this list and I looked to see to what extent AllegroGraph would fit into this picture. And so the first thing is, do we have a schema? Well, and what kind of schema information do we have? Well, we do node typing. I saw with my little example a few seconds ago that I can do edge typing. I can add attributes to nodes and attributes to edges. RDF supports directed edges because I say A trusts B, or I can say B trusts A. I also can do undirected edges, although I would have to use something like a symmetric property, or I have to use generators. That's a technique I'll talk about later. We do restricted edges. I didn't know exactly what people meant with it. It looks like it means islands in your graph. We do loop edges where you can point back to yourself. Attribute indexing, yes, we can put, well, we can do that. We don't have a starting node, although we wonder whether that's a database property. And finally, yeah, we do schemas, and although in RDF land we call them ontologies, and you can use them or you don't have to use them. So it's fairly flexible how we deal with schemas. Then for queries, we provide various languages. You can write code directly in Lisp and Prolog, or we can do JavaScript in the server. And then, of course, there's many languages on the client side. And there's the traversal part in this schema that I showed you a few seconds ago. And I think people meant by traversal that the internal representation is using a list structure or hash structure where things point to other things. Now, we don't do that in the tuple store, but we have additional techniques, and I'll talk about it later, where you can actually create traversal structures. And we even have a language called Jig, JavaScript interface for graphs, that does traversals, at least on the query level. Then database stuff, well, AllegroGraph is a 24/7 database. I'll later talk about a use case where AllegroGraph is used 24/7. It's transactional asset, fully indexed. It's distributed. We have all kinds of caching techniques. The 3.3 version is embeddable. The 4.2 version is a server version, which is not embeddable. And we have, well, migration framework. I guess in that they meant, can you have techniques to get from a relational database into a graph database? And yes, we have various techniques listed on our website to do ETL to get from a relational database to a graph database. And then the utilities list, we have lots of utilities. If you want to use a shell with the triple store, you can go straight to Lisp, or you can start up a Python and use that as a skill. We have a Groovy interface, so you can, in Java, kind of step-by-step work with the triple store. And then I'll show you Jig, which is an in-server shell. Then there's the issue of algorithms. Can you write algorithms in your graph database? And, well, so many ways we can do this with JavaScript, for log Lisp, or whatever you want. We have benchmarks, but only for RDF stores, not for and for reasoning, but not yet for the graph database. But that's mostly because the graph databases don't really have a big benchmarking culture yet. I guess that will come. We REST and JSON as our protocol. Let's not go too deep on these things. You already saw Graph, the GUI that we have. So we provide the IDE integration. We have an administration tool, AG WebView, where you can do all your management features for the database. You can import and export your data, and then we have various loaders just for loading RDF or for loading graphs. Then, of course, all the languages I showed you before. And now let's do some more fun stuff than going through slides. Let me give you the first demo. Let's see. So what you see here, let me see if it's still working. Okay, so I saw from the list that various people have been attending my webinars where I gave my pharmaceutical demo using various linked open data triple stores from, various linked open data sets having to do with drugs, diseases, clinical trials, etc., etc. And I opened that database on a server, and one of our colleagues, Joshua Chenevier, wrote in JavaScript something that resembles Gremlin. Actually, let me go back to the presentation first. So what we have is this graph traversal language called Jig. It's called the JavaScript interface for graphs. It's heavily inspired by graph traversal languages like Gremlin and Pacer. But in our case, it runs directly in the server. The fun part is it can use all the APIs from AllegroGraph, and it's a fairly interactive way, a fairly friendly way to get through your graphs. So again, here, so on the left-hand side, I have a Jig session open, and then on the right-hand side, I have the JavaScript that implements the Jig. And there's something wrong with the service, so somehow everything takes about a second longer than normal. What you see here is the first expression where I say, this expression, I should start with this expression first, actually, just for completeness. So what you do here is you get the beginning of the graph. So you set the variable g to the entire graph of your database. Then what you can do here is you say, okay, give me the first 10 triples. So now you get only the first 10. And then you say, okay, of the first 10, give me the label. So I guess some of the people on the line will be. However, this is all the same as, yeah, so it's kind of boring. So let's find some distinct ones. So we can go here. So we say, okay, give me of the triples the first 100,000, give me the label of those, and then give me the distinct labels in that. And so what we see then is that for the first 100,000 triples we get a whole bunch of distinct labels. Yeah. So here's one. So so this is a factor of results, and number 249 is that this is a synthesis reference. Okay, let's get a particular type. So if we go back here and we go to say 6. Oops. So R6. We saw that the 6th label was RDF type. Yeah. So what we do here is we say, get me number 6. So here say type is the 6th element of this entire expression. And so now we get the type. And so now we see that we have this particular type here. That's a variable. And so now we say, find all the distinct types in the first 100,000. So read this like this. We say, okay, given the graph, find all the triples where the edge name, the edge label is type, or in triple land where the RDF predicate is type, and that was the type that we found here. Then look at the objects of these triples, give me the first 100,000, and then look at the distinct types. So I can look through this, and I will find, I guess, 4 types. Yeah, so I see 4. So we find genes, drugs, targets, and secondary outcomes. Okay, so now we have these 4 types. And let's look at the first one. So we go here. We say, okay, let's take the number 1 here that we have. So here you see on the left-hand side we have drugs. So we set the variable drugs to the first element of this list. Again, by the way, I apologize for the time it takes. I think that in a month or 2 we'll give a seminar just entirely dedicated to JIG, and then everything will, like normal, take just a few milliseconds to return. So we have drugs now, and now we want to find 10 instances of drugs. So this is the expression to find those 10 things. So you put drugs in the pipeline, then you find all the incoming edges where the RDF label is type, then you find the first 10, and then you take the tail of these edges. Yeah, so here we have 10 instances. You see these things have numbers. These are 10 instances of drugs, or whatever. This is a standard number for these drugs. Okay, so now we go further. So now we have a set D with these 10 instances. And I can say, okay, given one of these particular drugs, find all the vertices within 2 steps of D number 0, and then also store the number of paths that you needed to get to this particular index. So when I find, so I can go here. So now I make a set D0, which is a vector of all the vertices within 2 steps, and for each vertex that we find, we also kind of have a strength weight. Yeah, so for example, we see that for drug, say for water here, there's 4 ways to get from this particular drug to this water here. Okay. So we take another one. So we take D9. So, and then what you want to do is find the intersection between the 2. Yeah, so you look at the 2 factors, the factor D0 and D9, we had all these vertices plus the weight of these vertices, and then you do an intersection where you look at the weights. And so we do this, and here we see, for example, that water is the intersection between these 2 sets, and it has a relatively high weight of 4. Yeah, and the word ingredients is a very strong common vertex between these 2 sets here, because it has the weight of 8. Anyway, so this is a very simple demo of JIG running in the server as a way to explore your graph. Is there any questions about this so far? Okay, good. Yeah, so we have a graph traversal language for AllegroGraph, and I just gave you the jig demo. And then the other thing is we have many graph algorithms that we implemented for AllegroGraph. Most of them we wrote because we needed a social networking analysis package for a customer. And so we implemented many algorithms from this book, Social Network Analysis, Methods and Applications. Wonderful textbook. And basically what we did is we created a technique where that we call generators, where you create a function that takes one node as an input and then returns all the children of the node given a function or a set of edges that you're interested in. And to make things very fast, we created a thing called neighborhood matrices, where we can actually use these generators to make adjacency lists that will speed up your particular queries. And we have a whole bunch of these social network analysis or graph functions. Usually what I do, I categorize them in 4 different ways. I say the first one is how far is an actor 1 from actor 2? So we do degrees of separation, the shortest path, how far is P1 from P2? And we can compute the connection strengths between 2 nodes. We can, and I will show this in a second, find the groups that a particular actor is in. So you start with one person and then you look at the friends and the friends of friends. Or we can look at fully connected graphs, so we get the clicks. We can look at a group of people, a group of nodes, and then we can compute the importance of a particular node in that group. And we have many different ways to compute the importance. Well, very cheap and usually enough is to just count the number of incoming and outgoing connections. But this is also a very popular one, like the active degree centrality, which means I have the most connections in the group, so I'm more important than anyone else. Anyway, we'll send this thing around. Let's not go into social network analysis this morning. And then the 4th category of social network function is, so I look at a group, and then you want to find out what is the most important person in this group, and is this a cohesive group or is this not a cohesive group? Yeah? And then we made all these social network functions and these generators available through every client language that we have. So this is, for example, how you do it in Java. So this is a generator that is an input one node, output a list of nodes. If you go to our website and you go to our tutorials for social network analysis in Java, you'll see how we can create a generator. Anyway, let me give you a demo instead of going into the technology here. And then we have a whole group of functions that we can use in every client language. For example, ego group, you start with one particular person, you choose the generator that you want to apply to the actor, you go a number of steps deep, and then you give the results back as a group of people. And we have ego groups, you can compute clicks, you can do statistics on how important the person is, you can compute the group centrality, etc., etc. So let me show you a demo of that. So I go back here, let me kill all of this. And then I go, I guess, here. Let me go here, close all tuple stores. And then, so what we use as a data set here is all the links in the DBpedia that have information about movies and actors. So we just made a subset of movies and actors and loaded that into a tuple store. We have that data set available on our website. It's entirely RDF. And so I can open this. I already loaded this database. And I open it. And then what I have to do is I have to register some namespaces so that I don't have to type them in all the time. So now I have 3 namespaces. And let me first look at the data for a second. So let me go here. Where's graph? Here's graph. Yeah, so let's look at a fairly famous actor, Arnold Schwarzenegger. Yeah, we can look at Arnold. And we see the RDF representation for Arnold from the DBP. His birth. He's a type, which is this really weird type with this actor and a big number. And then the things where he was an actor. Well, I think he was a producer here, or here see the things that point to him. Let's just go here. People that he was in. So this is Emma Thompson. Anyway, I'm just clicking around in these movies. Let me look here. So what we see here is we went from Arnold to film to Emma Thompson to another movie to Joe Richardson, etc., etc. I can go back. So here we have Arnold, and now let's do some graph search. Let's also find Charles Boyer. So here's Charles. And let's see if we can connect them through the starring relationship. So I now select the predicate that I want to use for my network search. And I can say, oops, this 96 path. So I get this thing here. Let me do this. Yeah, just select some shortest paths. And then here you see some graph from how to get from Arnold Schwarzenegger to, where did we have this guy? I lost Charles. Oh, here's Charles. Okay, here it is. Yeah, so here you see some shortest paths. So this is the data set that we're working with. So now let's go back to Emacs. And somehow, okay, here. So let's create the generator that I just talked about. So here we say, make a generator. Let's call it shared films. Yeah, where the input is an actor. And then we have a prolog function that gets executed and it will result in a list of other actions. I can do the same thing in Sparkle, by the way. Yeah, I can say select other films where there is a film. Let me get this as an argument here, that stars a particular actor, and they give me all the other films that also star the same actor here. Yeah. So let me execute this. Oops. So now I created a generator, and let me just, I can do the same thing for shared access, but let me apply this generator to a vertex. So for example, I have this particular actor here. Let's apply this generator to this actor. And so what you see here is that when I apply shared film to Charles Boyer, I get a whole bunch of actors. Let's see, length star, oh, 79 actors. So that's roughly the branch factor in this database. It's a huge, huge branch factor. And so then let's use this generator in a function. So for example, we have depth first search between Charles Boyer and Arnold Schwarzenegger using the generated shared films. So basically what happens is you traverse the graph, which is much bigger and has many properties. But when we do our depth first search, we only look at this relationship between the actors. Yeah, so we do a depth first search, and when I execute it, then let's see, how many do we get? We get a path from Charles Boyer to Arnold Schwarzenegger that is 17 steps deep. Yeah. So basically, it's just doing depth first, so left first all the time, and you get a huge length, which is of course nonsense because we saw on the screen that it's much shorter. So what Graph uses, our graphical tool, is this technique, bidirectional search, which is a graph technique that is optimal in terms of time and space usage, where you start at both ends. So you start on the left, at the start at the end, and you basically do a breadth first from two directions until they somehow meet in the middle. So we do this, and then we get the shortest path from Charles Boyer to John Gielgud to Rod Steiger to Arnold Schwarzenegger. Yeah. Now, how long does this take? So The branching factor is huge in this movie. If you just compute it, if you say EXPT, you go 4 steps deep and say 79 to the 4th, you get already a lot of branches you have to check. But bidirectional search goes fast, and that can do 100 times in 4 seconds. Although that sometimes is still too slow. So we have other techniques. So we have 2 techniques that if you work with telecom data sets, for example, where the branching factor is also between 40 and 80 for the average person. Well, if you want to do a graph search, that can get huge. And so there's various ways we can speed it up. One way is to make a special index for shared films where we don't have to apply the prolog function, but we can just make an adjacency list. We can make an adjacency list out of this relationship. So I made a special index, and now I create a generator again using this particular index. And now if I do the same relationship again, then I get done in about 2 seconds. So it's sped it up with a factor 2. So for a small database, from 4 to 2 is not much. But if you use this on hundreds of millions, it's really, really huge. Then another technique is that we use is, say you have a particular graph and it's huge, then sometimes it makes sense to first, and you want to analyze a group of friends, then it actually makes sense to take a person and first find a subgraph around that person, and then once you've done that, turn that into adjacency matrix, and then do the search within that smaller group. So you make a subgraph, and that subgraph in this case is already 13,000 people because I went 4 steps deep. And now I create a special index that only looks at this graph, and I call it MBM. So now I have a neighboring matrix. So I pay the first time when I do this matrix, I do pay, but afterwards all the search in that group will be very fast. And now if I use the same bidirectional search again, I get it almost in a second. Yeah, so this is a great technique to limit your graph searches in a practical way. Oh, it's already 40 minutes. So we integrated this technology in Prolog and in Common Logic, so we can just write code, and in the future we'll also include it in Sparkle. And then you just embed all these functions to straight in your query language. So that's very powerful. Like most graph databases don't have a declarative way of doing a search, but with what we have with Sparkle and Prolog, you can do declarative search and still get your graph algorithms too. Okay, so I'm already underway. You want me to still do the sandbox case? Okay, so what you've seen so far looks all like toy stuff, but actually this gets used in many different industries, and we have a whole list of customers that I can talk about. But one customer that we have is called MDocs, the biggest third-party billing company in the world, and also probably the company that sells most CRM software. And they built this whole new semantic platform to know everything about every single customer. Yeah, so it's a new kind of business intelligence. Yeah, so most traditional business intelligence can tell you everything about the average customer, but actually nothing about why this particular lady is bad at it, is angry at the telephone. And so what this technology does, it allows you to take about 40 databases that you need to run the telecom operations and ask many different questions. So basically we put a brain on top of all the databases so that now within one click of a button we can predict the 3 most likely reasons why a particular person will call the call center, or we do have the last 10 events for a particular event. We can compute the likelihood that someone will change from one telephone company to the other. We do social network analysis here, so we can look at the 10 most important friends that a particular person has, which is actually very important, because if the most important person in a group of friends switches to another telephone company or switches from iPhone to Android, then most likely other people will follow. And anyway, so we do a lot of new functionality on top of this. And the fun part is it's all in a graph. Yeah. So what this thing shows that on the left-hand side you have all these different databases, but we abstract that and turn it all per customer in a whole bunch of information about you as a particular customer, and have more like subjective information about you as a person. This is the architecture. So we go from raw databases. We turn things through an ontology into triples. That goes into a pub/sub architecture where a decision engine will read in these triples, look at things, and for example, if I don't pay my bill, then their judgment about me being a good payer goes down to me being a moderate payer. Yeah, so that's now a new element in the graph. That actually gets into a Bayesian belief network to make predictions about me. Out of that we get new triples, and that then gets stored in the AllegroGraph. And then it can be used in various places. But here we're talking about literally hundreds of billions of trillions of triples. And so we recently had a presentation for Gartner where they said, okay, so why are you guys not using a relational database for this? And then MDocs came up with the following reasons why they used the graph database of Triple Store and why they used the AllegroGraph. And here you see many things why people prefer graph databases. Yeah, it's a very dynamic data model. Relational databases, it's hard to add new relationships on the fly. Something like Teradata, it's really hard. Only NoSQL databases can do it a little bit. We can do inference. Yeah, no other technology can do the inference. Very much real time. Relational database and NoSQL are probably still slightly better, but we're very good at it right now. Scalability, semantic capability is something that no other database has. Dealing with structured, unstructured data is also better in a graph database or Triple Store than any other database. And the total cost of ownership for MDocs was lowest for a Triple Store or a NoSQL database. And then finally, so I'm almost done, please come see us at MTech. I'm going to talk about how we now do experiments where we do queries on more than 1 trillion triples. Basically what we do is we take complex Sparkle expressions and we turn them into a query flow language, a graph itself. So we use a graph structure to query a graph database. And so what we see here is we have all these modules like merge modules, left join models, right join models, split models, filter models, string lookup models, and they get distributed over literally hundreds of machines to give a quick answer to these complex Sparkle queries or graph queries. And that's about it. Summarizing, yeah, I showed you various reasons why we do all kinds of graph algorithms. We have graph traversal languages. But graph databases in general deal much better with long strings for queries than graph databases. Unlike graph databases, we do offer reasoning, and one thing is that RDF databases deal better with graphs that are larger than memory. Most graph databases live in memory, and they work wonderful. RDF databases deal much better with those situations. So that's about it.